So we are live. Okay. Hello. 1, 2, 3. So we are live. Okay. Uh, so this is the day one of me building my own CPU emulator with C from scratch, and I have never done this kind of thing before. And the end goal is to emulate a CPU, to be able to emulate a CPU like x86. And I don't have much idea. I want to figure it out on the way. I know C, but I don't know much about CPU, internals of CPUs. So this will be a great learning opportunity for me. And I'll start small. I'll start with the 6502 microprocessor. So it's a very old microprocessor. Mm, I will start with this one. So it was released in 1975, 51 years ago, and it was made by Motorola. So I want to start with this because it's a little easier, I think, for me. It would be easier for me to emulate this first because it has less instruction sets and it is less complex than the 8 so I cannot speak. 1886 architecture. So let's start and see what happens. So I have a reference manual here for the instruction set. Before that, I think I should try to understand the basic architecture of the CPU, how this works. So this is a reference. I'll put it in my description, I guess. And so let's start. So basic architecture, the 6502 microprocessor is a relatively simple 8-bit CPU, okay, with only a few internal registers capable of addressing at most 64 kilobytes. Okay, it's small b. Is it bytes or bits? Because when small, it means bits. Let's see. The memories are it's 64 kilo. Microprocessor. So it's bytes, okay. And okay, they should have put it like capital B because it's bytes. So whatever. Of memory via its 16-bit address bus. So I understand the basics how a CPU works. So address bus, from my understanding, is let me pull up the diagram first. Okay, that one. So these are the address. So this is the CPU. Okay, and these are the address buses. These A0 to A11 and 15, 14, 13. Oh, sorry, 12 to 15. Uh, means 16 address lines, and they directly connect to a memory. Uh, as far as I know, uh, this type of CPU connects to EEPROM, electronically erasable, was full form. EEPROM. EEPROM. Electronically erasable programmable read-only memory. Yeah. So they connect to a memory, and these are the data lines. Means they say from the CPU. CPU says from these lines, okay, I need this address. The memory, the data from this address, XYZ address from these lines, and this is basically 2 bytes, and the memory returns the data through its data line, and this is the data line that connects to the CPU. And I don't know if I'm able to like explain the whole thing. Okay. Less complex than data from this ad. And I don't know if I'm able to like explain data from this ad. And okay, my stream is saying something like we need to change the video resolution. Current resolution is uh this which is not supported. Okay. There is no viewer, so I cannot like ask anyone to check. Um, Let me check it. Um, Let me check it. Oh, it's working fine. Then why is saying that? Let me check it. Oh, it's working fine. Then why is saying that? Okay. So let's continue with the manual instruction manuals. Okay. And the processor is Little Indian and expects addresses to be stored in memory. List significant byte first. Okay. So Little Indian is basically let me show it. Little Indian. So in Little Indian CPUs, what happens is CPU reads data from memory in reverse order. Simply, uh, if this is the data in any of the memory location, it will be read from the lower bytes first. This will go first. This CPU will read this first, then these 2 bytes first, then this two, then this two. You can see here. So let me start making some notes. Notes.md. Okay. Basic architecture. We know that this size is okay. It's a big CPU. The memory size will be should be something like 64 KB bytes. Where's the, what is the actual file? 65. This is the bytes memory. Then we have little the it is the first page by the first 256 byte page of memory from this 000 00FF is referred to as zero page. Okay, so page is uh like unit of memory for operating system or CPU. What is a page in memory? So a page is a fixed length contiguous block of virtual memory, typically 4 kilobytes, used by operating system for memory management. Okay, and page size for is this page size 256 bytes page size, and memory is divided in zero page, referred to as zero page. This is focus of and this is the focus of a number of special addressing modes that result in shorter and quicker instructions or allow indirect access to the memory. Okay. Second page of the memory, 100 to 1 FF. So 100, 0, 1, 0, 0 to 0, 1 FF is the next 256 bytes. Reserved for system stack. This is stack. Um, zero page is from 0x000 to 0x00FF. Then we have the system stack. System stack. So stack is basically where the current running functions instructions are loaded, and the size of this stack is similar. Zero one zero zero 0x1 FF. And this is reserved for system stack. And what is a system stack? For to be sure, system stack um, of 6502 microprocessor. Microprocessor utilizes dedicated to 6 byte stack, hard coded or to memory page 1, 0, and 1. Located at address. This is the first out. Okay, as usual, like normal systems stack in here, it's last in first out. And so in pointer with an 8-bit stack pointer, which still managing the top of the stack by holding the low byte offset from location fixed to image. Pointer S register. So basically, we have the full memory. For example, we have the full memory, but there are certain areas in memory that we cannot uh, modify. We can modify, but we have to specifically like put them in a way so that the CPU can read from it in a specific order, and the CPU can execute from them. Definitely, the concepts are not totally clear for me. I need to dig deep into them. Notes deep into them. So I started streaming, but I haven't recorded anything. I will start recording from now on. I'll also give a little uh, introduction again. No one is watching anyway. So, this is the day one of me building my own CPU from scratch. My end goal is to build a CPU emulator, not CPU. Oh, I missed it again. So this is the day one of me building my CPU emulator from scratch, and the end goal is to create a CPU emulator for x86 architecture. But before that, to understand how a CPU works better, I will try to emulate a more simpler CPU or microprocessor. So I will be emulating this microprocessor. It's a Motorola chip, 6502 processor, and many people have done this before. And it was released in 1975, 51 years ago. Uh, It has a relatively low number of instruction sets compared to x86. And so that's a big plus point for me because now I have the opportunity to like understand a more simpler version of CPU. And definitely the x86 is different from this one, but still I will learn a lot that I can use and reuse to maybe build a emulator for x86 architecture, and it will help me. So I will be starting with the basics, very basics. So how a CPU works is basically a CPU executes or does something XYZ, for example, adding two numbers. And it needs the instruction for them. It can do stuff, but it doesn't have any memory or it doesn't have anything to point, like it doesn't understand what a number is or anything like that, but it understands instructions. Okay, do this, do X, do Y. And for that, it needs memory to load the instructions that it needs to execute. And to do that, it will read from something like a memory. And this CPU, this is the like diagram of the CPU we are building, emulating, and it has 16 data buses. So what are data buses? Data bus is basically uh, if you are familiar with pointers in programming, C, uh, what is a pointer? Pointer is an address to a memory location that has some XYZ data, for example, int. And these data buses are physical representation of the memory addresses. Simple. And this this connects to a memory directly. And the memory, when there is data, for example, this is 2 bytes, 16-bit, and it's a 16-bit processor. 16-bit processor. So the data width is 8 bits. it means it can read 8 bytes of data at once, bytes, bits of data at once, and it can start from the address width is 16 bits. Okay. So as I was saying, it talks to the memory through this lines A0 to A15, and the memory returns data through this lines T0 to T7, 8 lines. And because the CPU can like read memory address from 000 to like FFFF, means like 2 byte like 16 bits, uh, it can have a memory of 16 kilobytes, so 64 kilobytes. And yeah, it's a little endian processor. And I have already like I previously I have started the stream and I forgot to like press the recording, so I am just restarting the introduction. Wow. So, and I also took some notes from the previous part. And this is the memory size, maximum memory size it can handle or read from, and it's a little Indian processor. That means when the CPU reads something, it reads it in a reverse order simply. So if this data is in the memory and it can read 1 byte at a time. Okay, the CPU can so the CPU can request memory address of 2 bytes, but it can read 1 byte at a time for one word. And this is the first byte, it will read like this. Then this is the second byte, then third, and then the fourth byte. And as you can see, it's in reverse order. And that's for Little Indian. And the page size of the like memory for this CPU is 256. So what is page size? Page is basically if I go to the page size, what is the page size? So the 6502 processor uses a page size of 256 bytes, and page size page size is the fixed size of block of data used in virtual memory management, typically set to 4 kilobytes, or sometimes 16 kilobyte for larger to improve efficiency by increasing page table overhead. Okay, we'll go into deep about this paging thing later. I want to start with the very basic, definitely. And the only other reserved location, so there are 2 pages that are reserved for the uh, CPU. And these parts are, as far as I understand, one part is for system stack. So stack is basically a memory location, simply put it in a way that has the instructions for the current that has current instruction and some not variables, yeah, something like that. I have to go deep into that. And after the CPU starts, it starts. Okay. Architecture and registers. So we have different types of registers. So this CPU has the like 7 types of registers. So registers are temporary, like think about it like a variable for CPU. CPU has like, at first when the CPU starts and it starts to execute stuff, needs some place to hold small pieces of data, and these are the places where CPU holds them. I think I should start with the implementation part so that I'm taking notes and looking it all together. Include std io h what went wrong to like ind main. So let's start with the registers. We will put them as a struct inside a struct. Struct. Um, so this is basically a CP. Okay. If we think about it, this is the CP because it has the program counter. Where should the CP look for the next instruction? Status registers, stack pointer, the the current instructions location, and in the memory that needs to be run every cycle. So let's start with our CPU 6502, and we have it's 16-bit. That means we can use something like, and it's cannot the value cannot go down. So we have to use something like we don't need negative numbers in program count. int 16p, then EC, then we have a we have the accumulator HC, which is 8-bit, and then we have the X register, X and Y registers. What are the called? XR. Okay. XR, we have YR, we have SR, we have SP, stack pointer. So we can put something like X available type ID. I can put some comments here. This is the program found when we have the vector x register y register we have the status register we have the stack pointer something like this. I will also import, should I import them all? I think I should just define them. Define true and define zero. Oh, so we have to, this is the state of the CPU. In any given moment, the CPU has these values. Okay. And now we need the memory. So memory size is something like memory size is this. So what we can do is we can also do const memory size is it's the thing U ID 16. So 16. This is again Einstein short insert conversion from into I don't care for now. Yes. Still no one is watching. I will just use me and page size which is 256. Now you can do something like initialize the CPU. Drop CPU and we have say CPU. Yeah, that's it. We want a function to start reset. So it's called reset. So for some reason, yeah. So reset means all the values are zero and program counter is set to a specific location. processor status has these flags. I'll implement them definitely. Not now. Instructions. We will definitely start with no op instruction, like the very simple processor status. I think I should also implement the processor status. So what are these? First, accumulator is the main register of CPU. So its content is typically used by arithmetic logical unit for the first operand, and results are deposited in accumulator again. Okay. Thus its name, as it contains typically content typically is typically used by the arithmetic logical unit for the first operand deposited. Then we have the objects, so X and Y registers. These are auxiliary registers like accumulator. They can be loaded directly with values both immediately as little constant from memory. Additionally, they can increment, decrement, and yeah, they pull down like the memory location of the current instruction. As I say, um, it contain is automatically step up. Okay. So this, every CPU has cycles. So when the CPU gets power, it starts, and every clock cycle, every time the clock ticks, basically external clock ticks, program counter goes up by one automatically. And independently program executed as program is executed and is modified by branch and jump operations. Okay. Branch and jump operations. Okay. As it must be able to address the full 16-bit address range of I. Only the only 600 register in. Oh, so I hope it makes sense. Made full sense for me now, right now, as I'm speaking. So the program counter needs to be 16 bytes. Why? Because the memory is 64 kilobytes. And to think about it, to be able to count from 0 to 64 kilobyte numbers, to count to this number, you need 2 bytes. Okay. This is basically 2 bytes. Exactly. And that's why this is the maximum value. And this of the memory size. And that's why it needs to be 16-bit. And that's how 32-bit processor also works. Like it can read up to what is the memory they make for it's something like 4 billion or something like this that for the 32-bit processors. It's 3 GB. This value. This is the maximum address a 32-bit processor can read to. This is the max limit, basically. And the data it reads is 5. stack pointer points to the current top of the stack, or rather to its bottom as the stack grows top to down. So the stack grows top to down, and it means uh, the first thing it gets when you put something in it, it is the last first thing to get out. Okay, last in, first out. And if you think about it intuitively, uh, it has to go downwards. Okay. If you don't put anything and you keep removing stuff from the stack, it will go down because leave last in, first out. This is exactly what the stack overflow sign is. You are removing one by one item. Stack, stack of paper, stack of cards, etc. Then we have the status registers, still recording. Oh, we have one like. Yay! I think it's my wife. She is not even watching. No one is watching me. I'm alone. Even my wife doesn't watch me. The status register holds the status of zero processor consisting of flag reflecting zeros of previous operations configuration flags like discipline, locking, interrupts, or setting of binary encoded decimal CD carry flag. Okay, we can handle this maybe later. Interesting. That bytes, words, 16-bit words, low line, high byte, even little Indian. Just when version follow instruction codes, sign values, complement, sign values are whose complement, sign in 5-bit 7. So this region of memory. So I need to go deep into the tools complement part, this part, PCB. But before that, the memory region at the end, very end, there is reset vector 16-bit reset vector. So start and reset operations, and active low reset line allows. So this we're talking about the physical chip. So active low reset line allows a low processor allows to hold the processor in a known state where the system is initialized. Okay. As the reset line goes high, the processor performs a start sequence of 7 cycles. Okay. Start sequence of 7 cycles. At the end of which the program counter PC is read from the address provided in the 16-bit reset vector add. Okay. Low byte, high byte. Okay. Then at the 8th cycle, processor transfer control by performing a jump to provided addresses. Okay. So first, the CPU does 7 cycles. It does probably nothing. Uh, does nothing at that time. And after the 8th cycle, it reads from here these two addresses. When you press the reset, for example, there is a button. No, there are no buttons. There are just pins that you hold high or low. And when you tell the CPU to reset or restart, uh, it will read from these 2 bytes and these 2 addresses, and the value. So these are also addresses. The value from the address will be the point where the CPU will jump or go to. Okay. Okay. A little bit confusing, definitely, for someone like me who is very dumb. And I will check it. Am I still live? Will check it. Am I still live? Yeah, it's working. No one still, no one is watching. Yeah, concurrent viewers. Right now, someone is watching. I do not. So let's implement first. Let's implement the memory stuff. Memory read and write. Mm, we can do something like so. The memory always returns a value of 1 byte, and we can read the address is. Let me put it like this. I think that will make sense. More sense. So for read, IND, we can read mem, and we will return the memory address. Okay. So we need an address for this, and we will, the address is UINT 16 ADDR, and we need to define a memory. Okay. And how we are gonna do that is memory. So the memory is, we can for now allocate the memory as array. Think of it as an array, and every element of that array is 8 bytes. 8 bytes. Yeah, that makes sense. So we can take something like I8 memory. It's gonna be a pointer, and size we will use calloc, and calloc, because calloc returns. So with calloc we allocate memory, and calloc returns a zeroed out memory in simple terms. We can also use malloc, but malloc is way faster, no doubt. But for now, just for the sake of implementation, we will use calloc, because calloc uses calloc returns a zeroed out memory. There will be no data. If we think about memory of newly started, like fresh start, and we look at the memory of any computer, it's going to be 0, like, apart from some parts. We can set that parts. So first parameter is the size. The size is going to be 8. We would be using hard-coded values for this format. The count will be memory size divided by 8. We can constant 8. Word can define, we're just defining a word. So a word is basically a byte, and depending on different CPU architecture and systems, the size of byte can vary. The size of word can vary. So for all type of CPU it is 8 bytes. So we can do something like 0x. This is the return value 0, 0. Yeah. We also can do 0x FF. That will be better, I guess. 0x FF. And we have allocated memory, or we definitely have to free it. So we don't have memory. We don't want that. We want it to be secure and nice. 0 viewers. So read is something like memory. We are going to do some pointed arithmetic here. Read plus the address okay, and the write will be similar. Write mem. We need address. We need the memory. Okay, and that, and we want to return some kind of status, right? So for now, we will be returning the value of that memory address instead of the memory returning some kind of status, so that we know that the operation was successful or not. And how we are going to do it, memory. So we have to point to the address and also the value. So the data will be also int64, so int unsigned int, size of 8, data. Nice. So this is in memory, and essentially what we have done here is so how does a pointer work? First, I need to explain that. This is so this is a pointer, okay, and calloc is returning the starting pointer or the starting allocated memory address till the size of what the total memory layout means. Something like this. Yes. Yeah. So this is the first byte. This is the first byte of memory. Then we have the dot. We have the first byte. Then we have those. Then we have the last byte. The what is divided by. This is the last byte. Okay. And this is our array basically. Starting from 1, 2, 3. Right now it's everything is 0 because calculators zeroed out memory size. And if we print and tell you size of memory, we need a makefile. For now, we will be keeping the makefile very simple. One, build GCC. The output is main and main.c. And then we have run. Run is basically main. We can do main and it's done. Size 8. Why the size is 8? Gallup size count. Okay, so we did it wrong. The size count should be the first. Now, still the size is 8. Why? Let me see. We want to do something like that's the standard. Size of this. Size point. Okay. So here I'm just okay. I'm just printing the size of the point. I'm not actually the actual size, right? So we can do something like this, maybe with memory like when we first we will write to add just 0xFF last address. And we write the we write E, then F. We want to say A, read from memory for X. The prepare um, is data data. I'm using that for, I guess. I is zero and we use something like I let them equal to F E. You can say something like PC pointer to 0x E to start in E and it will FF and then 0x FF F F. There's no good P pointer. So A 65 is basically the value of ASCII representation of A, and then the B is 66. So we have successfully we have created some kind of memory uh, emulator. Uh, like it's a very basic, definitely, no, but oh, we have a viewer. Hello, hey, thank you for watching. So I think the next part should be setting up a loops, some kind of, and to be able to execute um, outputs, right? We will start with very basic. We have different kinds of outputs, right? But we will start with a no op, and as we can see from stack instructions. So from here we found out that this part was basically the reset after every reset. The CPU, okay, So after every set, uh, there is a cycle count, the 7 cycle of sequence. Say I cannot speak, man. Performs The process performs a start sequence of 7 cycles. 7 cycles of start sequence, at the end of which the program counter TC is read from the address provided in the 16-bit reset vector. So we use a memory layout. So for now, what we can do is we can write probably a programmer function that will, for now, when we call that function, it will manually like set up our memory address space, right? Uh, it will set up the part where it reads. Uh, so it will be, for now it will be all zeros, but two or three instructions. One instruction located in this region, and the next region is like FFFD and FFFC. These two regions, and both will translate to another address space. Okay, and then that will be read as mm, yeah. So, I think making it. So you asked. So someone asked, what am I doing? I am building a CPU emulator, and my end goal is to build a x86 CPU emulator. But oh, no one is watching. So what's the point? Okay, I will explain it later when someone comes and asks me. It will be void, definitely, because we don't need to return anything. We can do something like a status, but not now. We usually kind of status set up memory date memory return now. So we'll do something like this. So C and E, they both we look at CDOX. I'll send them to 0, 0, and 0x. So this pipe will be the first pipe. This, so if we we need to change the memory layout to something better. 0x0000, and DBR access, and then we have the data. I think I should take it to another memory layout only where someone else is watching. So this is our memory layout basically. And this for now, we have FFF, FFF, FC, which is pointing to 0, 0, and then 0, 0, another 0, 0. Let me first create memory layout. That would be better for me. E, then FF, this is the N. So, okay. So start of memory and of memory. Um, and so when the CPU starts at first, it goes through 7 cycles, empty cycles, it does nothing. Then it goes and reads from these two addresses. First, it goes and reads this and this. So when it reads this and this, these two addresses become the stack pointer. And stack pointer and stack pointer has the like stack pointer is the new addresses for instructions. So here we will have the instruction, and this will be our let me so this because it's a little endian, the data will be related like first this and this, and this will be translated as this, and this that. I, I I'm mixing up things. Yes. Uh, so byte order, 8 bytes, low word in low byte, high byte, written little endian as range operating flow, print flow for instruction code. Sign value a two's complement. Sign is in 7 bit, most of it bit. Vector, low byte, high byte, low byte. low fi high five. So essentially, this means this part will go first. So this will translate to something like, so the memory will read these two segments and it will become 0x00, 0x01. 0x00. It will read it like this. It will read this and second this, and we have to reverse it. We can do it by whose complement. Whose complement. Little. So if you're still watching, I'm trying to like emulate a CPU, and first I'm trying to emulate a very old microprocessor. Uh, and yeah, so so as I understand, little bit is pretty safe. First, sorry, uh, first of you actors, second I actors. In your example, it should be it should be a fair zero XFL and it should be your example, it should be use. I have hexadecimal FF F3 coming in over a serial line in the manual. It states that it is a 16-bit Indian two complement value, and I need to convert it to decimal in C. However, I was trying to understand the little Indian part. I am now very confused, and so it's from 2013. Oh, back then I was a kid. Life was so nice. I was paid in school and everything was uh, also, is there any difference between a regular is there any difference between a regular 16-bit two's complement integer and the 16-bit usual ending two's complement integer? Okay, there is someone answering this question. As I understand it, little ending is LSB. Received first order address. Okay. Is received second order high schedule. Okay. So, but that, this I understand. But then, in your example, LSP would be the yeah, and LSP most significant byte. Okay. Less significant byte and most significant byte. I really don't remember. So the actual value in hex will be 2 hex left. Here is a snippet of code words. Okay, I can copy it. I'm gonna steal random people's code. I'll write a simple function to translate raw runs late 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 um, we will have a memory. So we will read from the memory and try to sample specific region of memory. So we want this function to be able to read from a specific region of memory and convert it back to normal decimal. And so we want a star type. Yeah. So address is always ADDR. Star ADDR UID 16 and ADDR. Then we have memory, which is 8 bits. Okay, I just crossed the 80 character mark. Is it 80 for me? Okay, I don't have that. I will make it better later. So now time to copy the code. Here This is really new. Input for serial number. So I think for now I'll keep it just simple. Convert it to value. Say 0x. It's 16-bit int. 0xff 0 0 0 1 0 0. That's the original text was I want. Did it grow? No, I don't think so. Little engine value will be something like 0x 01 0x 0. Yeah, it is one. Yes, I will. Yes. Each byte is in reverse order to its positional value. So with the bytes, mm, we don't want this part. We want, we want to keep things simpler. Um, Isolate little Indian. I think I'm doing wrong is let's go and just oops, see what happens. 0, 1, 0, 0. It converts it to it's doing a two's complement. At the end, we have to remove the two's complement part. Um, Converted value. Um, Original X, the converted value. In the list, the list in white first. How does it reverse it? Hmm, I can do that part, but how is it reversed? This event, this is the combined to shift 85 to 11. Oops. It's here. Screen shift, left shift, and right shift. Okay. Remember something like this. Origin to X. Um, um, A, E, E, um, release, hello, my viewers. I have two viewers right now watching me. Thank you for watching. So right now I'm uh, trying to understand like, how Little Endianness works. Like, I'm trying to write a translator, and uh, so far for the implementation, I have written like two functions for reading and writing memory. This is my memory layout for now. And if you have any questions, you can ask it. No problem. This is the state of my CPU. So definitely I will share the code. And yeah, they're doing something like I have the full value right. I need to focus it at once. So for that, what I can do is well, 16-bit little Indian basically. How how does this sort works actually? So it's not an array. Oh, it is an array. Yeah, it is an array. So I need to do something like this. Okay. So I need to read it from. Uh, okay. So right now I'm just trying to figure the whole thing, but whole, this part is fully, but it's not how it should be done. So in my memory, what happens is I have words of 8 bytes. Okay. And I have to reverse it, and then I can read it as decimal, right? So to do that, I need to read a chunk of memory. And doing that, what I have to do is so we will start at first. And LDR, then we need the new into so we have new blocks. I know do we need to do that? I think I should skip this part for now. I need to. So for now, I've invested a lot of time doing this. Shouldn't have done that. Uh, we have we have the set vectors. We are writing to we want that. We will be calling the setup memory memory. Now we will start our main loop while true is we have our loop. So after our CPU starts, there are 7 cycles. That does exactly nothing. Okay. So our closing counter closing counter, that is again which the closing counter is read from the address provided. We say vectors. Okay. Okay. So our closing counter is set after 7. Okay. We need ID unsigned long end. And we want to be log. Um, will be 0 at first. Then we will just if the lockdown is less than or equal to 7. We're just roughly doing this because the code may not look like this after we have done basic implementation, because right now I'm just putting out the ideas that I'm getting from reading the instructions. So yeah. Mm, Clock is 11. Plus plus. And let's see what does the continue to is it same as the Python or Golang? Statement. Synchronous jump statement use to skip current iteration loop which will lead to the next iteration. Will jump to the next iteration. Let's see. We will also jump this part, right? Um, when you log something long, unsigned long, unsigned it. There is log making and do something like starts with 1, skips 0. You know, something like I think we can make it more simple, right? We can start with 7 for now. So this is temporary. Temporary. Uh, to fix the log parameter logic. Okay. Okay, someone will respect brother. Okay, thank you. So I will stream for another half an hour. It's almost like 2 hours, and I have only very little. Like, I think no AI. I wrote everything myself, and the thing is, it's really weird because in 2.5 hours, if I had access to AI or something like that, I would have written so much more, and I would have done so much more stuff. So this is so interesting. Sort of. Let's move on. So after the 7th cycle, our program boundary process managed to control by the end of which the program boundary is ready. So, okay, this is a CPU emulator 99 bit different. I wanted to make quantum computer emulation, but I this is funny. Yes, I am deaf. Nice. I don't know how to like it. So I'm now thinking that how should I do the jump operation and like set the program out? Should I just implement it? Okay. Yes, I think I should just set the values. Okay, right. That would be fine for now. So this would be quick and first is FFs 0x FF F3 and so let you write it down first. Just looks like this. CPU grades. I need to translate it. Right. Middle instruction. CPU state. I can write a function. Okay. CPU state. Revision void. CPU state. And we can take the CPU and the CPU. So For now, we can do something like fix the, fix the clock counter logic. The start certain cycles, cycle insert I'll fix the reset sequence for later. I think I should first focus on the basic implementation. So, which statement? Okay. So we need to fetch the opcode, then we can start implementing the how the CPU will behave. So fetch, we can do something like we can do something like void fetch bytes byte. It will return empty and data. So something like 1.8 data is equal to read memory. So this is address CPU and this is program counter. Yes, this is our program counter, which the item we need also the memory and the memory, then the CPU PC goes 1 byte high as the clock cycle moves forward, it goes high. So after it returns, it goes higher, goes to the next address until you say to jump. Then it changes. We will definitely do that just in a bit. So yeah. Now CPU will fetch bytes. CPU fetches the byte. Then there's I think I need to have some way to see the chat in, so I don't have to change the windows. I have one monitor, one single monitor. So yeah, I think I need to do something like that. I will definitely do it not now. We have instruction now. We can do something like the load instruction. So I think the clock count is irrelevant for now. We can do something like, yeah, so that so we can do something. So for example, we can do something like a if clock count is equal to 10, we will break out of the loop and opcode. The opcode is basically fetch pipe from the CPU and memory. Saying okay, now we have settled the memory. We first, what is the PC? The program counter is 0, right? We need to set the program counter to this value. So fetch by we can say okay, we can create a reset function and it will just reset the value to this initial value of the program counter. So void reset CE CE and CE. Okay, someone will go, yeah, how am I going to do it? I will just CE PC is equal to FF 0x FFC and we'll start, yeah. Then all the registers, CPU, um, registers. So I have AC. We can start with the LDA operation to load a value to accumulator A, the register A. Okay. So A register, it will put a value inside AC, it's for this yeah. It will put a value inside AC. For now, it's 0x0. We just say almost everything. XR is 0. The YR is 0. SR is 0. Speed is 0. 1, 2, 3, 4, 5, 6. 6 registers, everything is 0. So 2, 0. So, implement that use local data media immediately in with the different types of loads. Oh, interesting. I didn't know that. There are different types of load. What? So, I think first I will implement the NOP, no op basically. Uh, so I think I should be because this is a part of the fetch and it is just CPU step. I should move it inside here. CPU step. We want to do no op code is EA. So it's EA. Okay. Just to be sure. Virtually lecture we don't keep that. No, what is the value? Okay, start defining stuff at the top. I think. Okay, I will. Constant fetch instructions. No, no, no. So what it is? It is a no p is equal to 0 x e a. Yeah. Then we want to do load a. I think load a. Load a immediately uh, puts the value inside the register A. There's nothing else. I need to get better understanding of these parts like zero page, what is it doing. If there are anyone who can, if anyone is watching and can point me to the right direction, uh, that would be great. By right direction, I don't mean to like give me the code or something like that. Just to get a better understanding because I'm dumb. I cannot. I'm here reading this one page of HTML website like for the last two hours. Yeah, 2 hours straight, and I just I'm too dumb to understand all this. So if there are anyone who can point me to a direction where I can get a better understanding about these parts, uh, yeah, I can Google it obviously, but seems like AI made me too dumb for anything. You know, code looks a bit cluttered. So the CPU step Elevator. Elevator is 9, A9, A9. Okay. So, go. How switch rows are. So, I can see case, and no B, no op. Then we do nothing. There's nothing. Case elite A. Now we have to do something. What we're gonna do is we will put we change the value of so um, instruction which height by this step. Data is which memory CPU C is equal to data. Okay. Now we single CPU step. Oh, segregation file. So someone asked, hey there, what architecture is the CPU emulator? So it is not x86 or ARM. It is so it is a very old microprocessor in 6552. It was made by Motorola. And what instruction set would use? Good question, actually. Microprocessor. Relatively basic RBSIS. Instruction 054. Mhm. Oh, wow. I I think I think the instruction set it it executes. It doesn't have any what do you call, specific name. If it has, I'm so new to this whole thing that I don't even know that. But it is for something like reduced instruction, reduced basic instruction, or something like that. Actually, I don't exactly remember the reduced. So it has total like 56. Mm, yeah, it has 56 instruction sets. Yeah, that's it. I have a segment flaw that I have to fix. What it is happening. GDB. Ooh, GDB. GDB. Mm, use instructions. So, so I had a segment fault. I think I missed it out somewhere here. Yeah, I was wrong with the. I messed up with the. Like, I took the CPU as a pointer, initiated it as a pointer, and like, and I passed it as a pointer. When I passed it, it was already a pointer, and yeah, so, I don't know what it is called. So I think I will do something else also. Log tag. We have PC, which is this. Sign in also. We have CPU and PC. PC, AC. I think I would just print it using something like print void print steps on the debug log. Debug log. I'm going to just call debug log. CDU debug log. I guess CDU debug log. Yeah, and dates CPU and CPU and date as clock counter. Okay, sign long long and long. Just take it. Let's see. Let's see. XR log and this speed. Now this 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 wide X E. Or you can just bring line break the end. Okay. Nice. Call it definitely. Bring CPU log CPU. I will just log. I have printed it outside of the loop. Now we have the full picture. Okay. Everything starts with the program counter. We can see X at first. It's, I think we should print the X was right. Now you do it. Yeah. Zero. Zero X. Everything is FF. Why? When I reset the CPU, why it's everything is FF? Shouldn't be right. CPU resets. What is the initial value? Reset CPU. Oh, I haven't reset CPU to reset CPU and CPU. Now the value will be zero. Everything is zero. Everything is zeroed out. No values. Scrolling down to when. So because at the first byte we so at first byte we read was this, right? This. And it said to go to this place. Okay. Stop. Say go to address 01. What did it say? They AC. First it was actually C, right? Okay. It is pretty late here. It is getting around 10, 30, 10, 11 p.m. So yeah, I will stop for now. Maybe I'll do 5 more minutes. Fix this bug, I guess. Mm, so I am CPU step this. Fetch memory. Move it inside print CPU. Block will be one just for now. But the AC is 0. Why? Shouldn't it be? After I set it, was there? Okay, okay. Maybe I get it now. See, still different resets. This program counter. Why the AC is not it's weird. Because memory is 0. Everything is 0. So I have to set 0 at 0, 0, 0, 1, 0, 0, 0, 1. I'll say, oh, I get it. I haven't put any instructions. How? I'm so dumb. TA. No. First try no. No. 2, 2, 3. Okay. So first it goes to this address. I think I should check the. I think I should check the fetch function if it is working properly. This is a memory and in terms of data. Okay. we want the to done print x ea reads one and e goes up d, then it goes to e, uh, and it goes there. Okay, it goes to fetch, fetches the e. Guys, I'm literally like reading my own code, like it's written by someone else, going up and down like that. Oh my god. Fetches a byte. That, that's the output.
Powerful gas stove has a
And then below technology fundamentals and memory of the emulator loads in data into the emulator, sets the zero, set flag if the loaded value is zero. Some people might help you track the flow. Yeah, yeah, good idea. I should do that. I really lack of you plug use or no ads. Okay, I will. I think I should. I'm just using uh, keyboard browser right now. I don't want to use the phone. I don't know why. I think yeah, I will definitely need to add more comments and set of manual which Doesn't it fetch one byte? Fetches. Fetches one byte. Next. Commenting should be better. For now, I'm living it like this. Same use did. Okay. Someone calling like software developer here. Java, C, CPP, you came up. YouTube home screen. For me, I'm Netherlands, international students. Oh, nice. That's great for you, man. Thank you for watching me. I don't know what to say or how to interact with the audience. Audience. I think I will learn. I think as I will do it regularly, I'll learn. So it's been around 2 hours. I think I'll stop for now. Stop for today. And it's 11 p.m. here. So yeah, this so still so what I have done today, I created a basic CPU structure. So structure that has the CPU state, current state of CPU. It doesn't have the flags it needed. I will maybe I'll do it tomorrow. Then I have created two functions for reading and writing to reading and writing the memory. And this function, I think I should go more to like file approach. I should write everything to a file, and then every time the program runs it, Emulator runs it, reads the memory from the file so that it will be better instead of like this. Definitely, I think I will do that. There are data sets in here. I think. Oh, I think I can find them. Data. Yeah, there are data sets already. There's not data sets like Google program memory. Yeah. Uh, Good luck with the comments, live streaming, extreme is cool. Okay. Definitely join my Discord. So I mainly make videos for Instagram. Yeah. I make short videos. I started making short videos, then I gradually moved on to like longer videos. Yeah. Because of work, cannot make longer videos regularly, maybe twice, once every 2 weeks, I can make one long video. So that's why I like almost every week post one or two short videos explaining, like breaking down topics, complex topics, not always complex topics, but yeah, low level stuff and security stuff. So definitely join my Discord. We have around 1,600 members, as far as I remember. Um, the we we have around 600 members, 16 to less than 1600, and I have the what do you call it? Mm, Discord. Discord. In the description, I have the Discord, and I will also add another. I'll add the home base to what do you call it? The Google Keyboard. I'll just update it now. I'll just add it. Add it. Day one. I think I will not add it in it. You add it commit day one, and just push it up with the date. So I have updated the repo. You can just go and check it out here. So I have updated the. I'll add some README file and the licenses maybe tomorrow. So yeah. So I also added the what the add the binary. I need to add some files that the formatting is not right. I have to do a lot. I will write it down. So add comments then fix for in step, then add get in all and the so I have like written it down. Yeah. Uh, so enough for today. I think I wasn't expecting anyone, but 14 likes is like, oh my god. It's it's like 1 million followers from 14 likes. Damn. The average view duration is 45 seconds. Okay. And chat rate views. Oh, nice views. It, the views, the chat, and everything exceeded my, what do you call it? Expectation. I expected zero, or maybe I at most I expected 2 or 3 people and 1 or 2 likes. But 14 likes only. It's like almost like, calculate. It's 5x what I expected. So yeah, this was the day one, and I will try to make a shorter video out of the whole stream. So 2 hour stream, yeah, 2 hour and 15 minute stream. So see you guys tomorrow. Maybe tomorrow I will not be able to stream for this long, but still I'll try my best. Uh, have a good day. Bye. Take care.